Okay, now we want to calculate escape velocity. We have our mass m1, we'll consider that to be a planet with a radius r, and we assume the planet to be spherically symmetric with mass distribution that's spherically symmetric, so that outside of the surface, this planet acts as a point mass with mass m1. And we're not interested in what happens on the other side of the surface, at least not for the moment. Okay, we want to calculate the escape velocity. What's the escape velocity? Well, that's the velocity at which, I wrote quick, at which the kinetic energy exceeds the change in potential energy from here to infinity. Okay? It exceeds the potential energy loss. Okay? When I say the delta PE loss, I really mean probably ought to say the PE loss from here to infinity. Okay, so the escape velocity from the surface, if we assume there are no non-conservative forces, of course, because if there are non-conservative forces, we have to take those into consideration. When we say the velocity at which the kinetic energy exceeds the PE loss from here to infinity, we're implicitly assuming that there are no non-conservative forces acting. So if we want to give this thing a velocity for which it will continue to go and never fall back, at least as influenced by the gravitational field of this planet, we simply calculate the potential energy change from here to infinity, which is very easily done. We just do the integral of negative big G m1 m2 over r squared dr from here to infinity. And if here is the surface of the planet, and let's say this is the Earth, but it doesn't have to be, so I'll use r sub e for radius of the Earth to calculate it for the Earth. Here's our integral. And we calculate the integral and we get this. So right there is our potential energy relative to infinity, okay? And that's the potential energy, that's potential energy here relative to infinity. Meaning that to get from here to infinity, we have to lose potential energy G big 1 m2 over r squared. And that's how much kinetic energy we have to have, because, of course, the change in potential energy comes at the expense of kinetic energy if there's no non-conservative force. Okay? No air resistance and no rocket engines, because that would be a non-conservative force. So we just give the thing enough velocity, assuming there's no air. And if there is a little bit of air, and there is just a little bit, we shoot a little faster to compensate for that. And it turns out that that's kind of unduly complicated because the velocity is so great that we pretty much burn up. But that, it doesn't change the theoretical calculation. So we set that equal to our kinetic energy, and let V escape, V-E-S-C, that doesn't look like a very good C, but it's a C. V escape is our escape velocity, then 1/2 of our mass times the squared escape velocity is going to have to equal this. Okay? So, and I really shouldn't have had the negative sign on there. Okay? So, we're assuming, of course, some projectile of mass m. Well, we just solved this equation for V. Excuse me, I had to hesitate there and remind myself of why I did this. It's been a couple of days. This is what we know. Okay? We know that G times m1 over radius of the Earth squared is gravitational acceleration. And we know that because the gravitational force on mass m2, which I've erased, would be equal to the force on that mass. Well, if we divide the force on that mass by that mass, we get its acceleration. So, and if we divide by the mass over here, the mass m2, we get this. So that we can make this conclusion and make a couple of other steps that I'm not going to outline because you should be able to do them. And in any case, we then conclude that the escape velocity is the square root of 2 big G m1 over RE, where m1 is the mass of the Earth, RE is the radius. So, what then is our orbital velocity? Well, orbital velocity is the V, is the V where the centripetal force equals the gravitational force. That's centripetal force on this side, gravitational force on this side. Solve this for V and we get this. Now we've done this previously, so I'm not going to redo it. You can, check out that result, but it's very straightforward. We set gravitational force equal to centripetal force and solve for V. We get this. Well, this is just like this except for the 2 we have here. And this means that your escape velocity is the square root of 2 times your orbital velocity if you're doing a circular orbit. And I didn't specify on the board here circular orbit, but let's be sure we specify this is for a circular orbit. Relevant to circular orbits, or actually any orbit, what's our potential difference, potential energy at distance r relative to the surface of the planet? Okay, so if we go out to distance r, what's our potential energy relative to the surface? Well, we can do the integral, and we find that there's our potential energy at distance r relative to the surface. I'll add that this is could also be the potential energy at distance r minus the potential energy at distance r sub e. Or the potential energy could be relative to any point. If we use potential energies at infinity, potential energy at distance r would be negative big G little m1 little m2 over big R minus the potential energy at RE, which would be negative big G little m1 little m2 over R sub E, which equals, I'm not going to write it out, you can verify that this equals this. And the reason it's always equal is you measure your potential energy relative to some position, and the only difference in the integral that you get if you go from a different position is going to be the integration constant. And when you find the change in the potential energy, the integration constant subtracts off in the manner with which hopefully you're very familiar when you do definite integrals.